Yeah, I'm going to talk a little bit about deep learning and what we do in chemistry with deep learning. And maybe I can also say a few words on why we do this particular topic and not something that sounds a bit more thrilling, like drug discovery. Is anybody here with a chemistry background? One person. And who would say that chem informatics is nothing that you've heard about much in your past? Okay, so everybody is reasonably familiar. You know, some people raised the hand. Thanks for that. So machine learning has like in many topics, a long history also in chemistry. The first books about artificial neural networks came out in 1993, published by Gasteiger and Zupan. And from there on, basically, then in those days very small neural networks, a couple of dozens or hundreds of neurons, became very widely used in all kinds of areas in artificial intelligence. I'm going to use all of these things basically interchangeably. I know there can be long discussions about the difference, but I'm not going to get into that topic. So this is now 30 years ago that this started. And we've recently reviewed what's going on in modern AI in molecular informatics. There is a lot of applications for deep learning in chemistry and related fields like protein structures, for example. Everybody has heard about AlphaGo and the fantastic things that it's doing. Basically, deep learning in chemistry is used to predict something about chemical structures. You can also use data to predict from the data which structure might have caused the data. And often you also want to start from the structure and predict its chemical properties or which reactions it's going to make. And in particular, the chemical properties are of big interest because people always want, nobody's interested in molecules, right? We are always interested in the properties that they had. Do they cure our headache, or are they making nice surfaces of tables or whatever? And a current thing, well, it's actually also quite old, but what's currently gaining renewed interest is knowledge extraction, because it seems that the large language models that are currently coming on the market or have been coming on the market and are getting better and better, and whatever is beyond large language models can be used to do knowledge extraction, which is something that we are interested about. My co-workers and I were particularly impressed by this event. Some of you might have followed this, or maybe all of you followed this. It always made it into the common press, the regular press that most people read. This is the ancient Asian game of Go, which was always deemed to be untractable for a very long time by computers. In the 90s, computers were able to, using brute force, to beat Kasparov, the then world champion in chess. But Go seemed to be, because of its high number of possibilities on the board, seemed to be untractable. And in 2016, the top I think in these days, the top player in Go was beaten by something called AlphaGo, developed by DeepMind, which is now part of Google. And he lost 4 out of 5 games against AlphaGo, and that was a huge success. And this was run on, this was a deep learning approach for evaluating the settings on the board, and there was a Monte Carlo search in the background, and that was run on a huge amount of CPUs and a large amount of graphical processing units to make that happen. But that was only a short moment in time, and shortly after they published AlphaGo 0. There was a nice article in Nature, Mastering the Game of Go Without Human Knowledge. And that was a fantastic achievement, because they essentially had 2 machines playing against each other. and they knew nothing but the basic, let's say, a handful of basic rules, where you can set a stone and how to evaluate there is no moving on the Go board, you just set stones, and how to evaluate whether one is ahead of another, right? And then the machines started playing against each other and learned. And they basically, within 2 days, they became stronger than the previous AlphaGo, which is the, I think this line here, and they became stronger than the strongest human player. So within 2 days, they discovered 4,000 years of Go knowledge and Go history, and that has really changed everything. And that was running on 4 TPUs, tensor processing units in the Google Cloud. So computational demand was shrinking dramatically. They later did the same with, I think, shogi and chess. And in all of these cases, very quickly, just by playing against each other, the machines learned how to play these games better than any human within a very short time, starting from zero knowledge, almost zero knowledge. And my friend Achim and I, here in Bolzano at the International Workshop of Open Molecular Informatics, we were thinking, can we do anything like that in chemistry? And the important part, as you might have noticed, is you need an almost indefinite amount of data to become superhuman in any field. And in most fields, we don't have that data available, basically almost nowhere. And so is there anything in chemistry where we can do something similar? And the answer is yes, but only if we fabricate data, if we create data ourselves. There is in no field enough data available, with very few exceptions. Proteins is a nice exception. People have started to collect protein data in the 90s, and now we have a sufficient amount of data available to train, but in chemistry that's very rare. So we came up with what is now known as the DECIMER project. To the people who are interested in this is known. And the idea was to fabricate a large number of chemical structure depictions to solve a problem that's called optical chemical character recognition. And why is that interesting? It's interesting because in chemistry, and elsewhere, a lot of the data that is interesting for scientists is still hidden in libraries like this on the shelves, in articles, in printed articles, where essentially chemical structures are represented like this. And this is just black dots on white paper. There is not much more information. A chemist can understand that. And in the articles, we see that we are interested in natural product chemistry, my group. We see that, okay, those are the structures that have been isolated from this fungus here. They are part of the polyketide structural class. They might have a chemical activity, and we have chemical names. And that's the type of information that we want to get out of the literature in an automatic way, because humans take, I know that from my work at KEBI that Dietrich mentioned, humans take a long time to extract this type of data out of the literature. The idea is to use these black pixels on paper and translate them back into a machine-readable structure. We have reviewed this, the state of this field. There is a little bit of a history, in particular with rule-based methods, which were working on the good old vectorization systems, which were already available in the 90s, and then putting the data together into a machine-readable form. But those rule-based systems, which were looking for lines and characters and then putting it all together, are very error-prone and were not really up to the job. A little side note on why we are interested in this. We are, as part of our efforts in the National Research Data Infrastructure for Chemistry, NFDI for Chem, we are maintaining the currently largest open collection of natural products on the planet. So natural products are small molecules made by living organisms. The database is called Coconut, developed by the two humans on the screen, and a larger team actually, to be honest. And we are trying to get the data out of the literature into Coconut by using the systems that I've been showing. Of course, in the future, we would love people to submit the data right away. We don't need to extract them anymore out of publications. But unfortunately, there is still a lot of treasure hidden in the literature, and we still rely on getting this out of the literature. So Coconut has about 700,000 molecules looking like this. They are typically quite nice and complex structures. We are interested in the organisms from which you can get the data, from which these compounds are isolated. So here's an example of caffeine structure. Caffeine has been isolated from those species here, and you want to know a little bit more about caffeine, of course, which is further down the screen. You can't see that here. We are maintaining collections. So there is a group in Australia collecting natural products from Australia. They are donating compounds. We have compounds from a particular lab, my colleague Jörn Piel at the ETH in Zurich. We have African compounds against cancer. So things in Coconut are organized in so-called collections. A colleague from the United States was interested in compounds in watermelon. So there are a lot of interesting collections that you can browse. And you can also, of course, look for a particular species, Papaver somniferum, the little beautiful plant that makes opium, and which contains all these compounds which are listed here. Right. I think in the interest of time, I'm jumping over this. So for this purpose, we aim to create a pipeline which takes an article, and this is really an image. Even if we get a PDF, we convert it to an image to get rid of all these artifacts that you get in PDFs. Segment the images out from the text, so we need a tool that I'm not going to talk about today, which does the segmentation, identify chemical images, then segment it out and predict back the chemical structure in the form of something machine readable. Now, again, these black and white dots on paper are not machine understandable, machine actionable. I'm going to talk a little bit on how we did this, because I still think it's a very nice idea, which my PhD student Kohulan had, who developed basically together with Otto, who is here, the whole system. And we are sitting here having fun because the system was behaving well, and we look like honey cake horses, many of the people here. Only the Germans understand that, the term, and maybe you can explain it to each other after the talk. So what was the idea that Kohulan had? Kohulan came across this famous paper by Xu et al., published in Archive, where they showed a deep learning system, convolutional neural network, followed by a recurrent neural network, and that system could take an image and generate a description of what it sees in the image. So here, this is a market scene, and the system generates a caption. A group of people shopping at an outdoor market. There are many vegetables at the fruit stand. That's a great achievement. Of course, the system has been trained on lots of annotated structures. And Kohulan's idea was we can do the same by showing the system an image of a chemical and generating a caption, which is a machine-readable representation of the image. This representation is called smiles. And allow me to do a little diversion into structure representations. everybody who had chemistry in school knows this type of 2D diagram. Again, it's black and white dots on paper. This is what chemists use as a machine-readable representation of this. It has a list of element symbols here, carbon, nitrogen, and so on. And there are 3D coordinates. Those are not important, really. And here comes a description on how those elements here on the screen are connected to each other. So atom number 10, which is the 10th row here, is connected to atom number 1 with a double bond. Atom number 1 is connected to atom number 2 with a single bond, and so on. So that's called a connection table. You can also draw this in the form of what is called an adjacency matrix. This is essentially all the whatever 15, 16 atoms here drawn against each other, and where you have a 1, you see the atom here is connected to the atom over here. And that adjacency matrix is obviously symmetric to each other. That's a very common representation. But what we used is the so-called simplified molecular input line entry system called SMILES, a very common representation for chemical structures. And the nice thing is it's one line. And basically what it does is you start at one point, you write down an O. This is not this SMILES, there are many SMILES. You write down an O. The next one that you encounter is a carbon, and between those is a double bond, which is represented by an equal sign. So you could write down O equals carbon, and then you continue to walk the graph until you have a representation. Branches, like here, are done by brackets, thank you, and ring closures are denoted by numbers. So between this nitrogen and this carbon here, we've got these two occurrences of number 1, you have a ring closure. And by this very simple line notation, you can encode a machine-readable structure of this 2D depiction. And that's the type of depiction that our system learns and regenerates. So obviously, this is a case where you can actually fabricate data. You will never have annotated chemical images extracted by humans out of the literature by smartphone or scanning, which are annotated with the machine-readable form, and you will never have 100 million of those to do training. Yeah? So you need to fabricate this data. So the idea was download all the molecules known to mankind from the biggest chemical database called PubChem. All of those hundreds of millions come in this SMILES form. Use a chemical toolkit, which is maintained by us, to translate this into an image of black and white pixels. Then we have pairs of these things, and those can be used to train a deep learning system to generate back the machine-readable representation. That worked reasonably well in the beginning, as always, not as good as expected. And I need to do another diversion. One of the you cannot only say that two molecular structures are identical. You can also say how similar they are. And in such a deep learning system, it's already a big achievement if the structure that was actually on the image and the predicted structures are relatively close. Let's say there is a metal group missing. Yeah? A curator can look at that and say, yeah, that's good enough. I'm using a structure editor to draw the missing metal group. Otherwise, the system has already saved me a huge amount of work. And that type of similarity between the real and the predicted structures is measured by something called the Tanimoto coefficient. Tanimoto coefficient 1 means they are, in terms of the Tanimoto, identical. They can still be slightly different for reasons that I cannot explain in the shortness of the available time. But the general Tanimoto similarity is also very interesting because it shows how close the system can predict structures related to the original structure. And in the beginning, we were getting something like an average Tanimoto coefficient of 0.6. 1 is perfect, and 0.6 is, well, not very close, not yet very close. But we were hopeful. We were using training data sizes of a few million structures in those days. And we were thinking, okay, if we increase the training data size and we take the few data points that we had with very little training data, how big does the training data size have to become to get anywhere close to a Tanimoto of 1? And something like 100% perfection of the system. Of course, you can't do that type of extrapolation seriously, but we were using it as a guess to give us an idea. And so it looked like anywhere between 60 and 100 million structures we would be becoming very good. Turned out we needed many more. Yeah. But the bigger problem was if you take a simple small data set of 15 million images and its machine-readable structures for training, and you train that for 25 epochs on a normal GPU in-house on a computer that's available to you. You take 26 days. If you go only to 45 million data set, and we needed 60, as you might remember, you are at 78, and it grows very unpleasantly. And this is too long for a PhD student. If you have training cycles of 3 months, you can't make many mistakes and your PhD time is over. That's not sustainable. But this was a fantastic project where everything came together, advances in software and algorithms together with advances in training hardware. While we were doing this on a Tesla V100, this bloody thing costs 10,000 euros, one piece, yeah, and it was the one that led to these long training times. Google came up with something called a tensor processing unit and made those available in the Google Cloud. And it made it available to researchers like us for free. These TPUs made things incredibly much faster. Sorry for the animations. They were made by Kohulan, and he loves those animations. We had things running on our V100, and if a particular training data set takes 30 hours, then the first available systems, TPU systems, were already going down to something like 8 hours, and on the latest hardware we were down to something like 2 hours. So from 30 hours to 2 hours. And that means that a training time of 6 months, which was a realistic time, went down to 11 days. And that's a dramatic increase just by hardware. Really a fantastic serendipity that this became available. Otherwise, we would not have been able to do this type of training, right? So eventually, we used up to 400 million images. That's completely undoable with normal GPUs. We generated depictions of those. We trained the combination of EfficientNet and Transformer. Those are all ready-made systems that others have made for us. We didn't need to do anything. And we could create a very efficient system for predicting machine-readable structures out of depictions like this, pixels, black and white pixels on white paper. The key, however, in addition to all of those things that I already mentioned, hardware advances, much better neural networks, the key was really in the way we generate the structures. The original version used the chemistry development kit, took the smiles, predicted a kind of perfect representation of a chemical structure. And that system did a good job as long as it got perfect chemical structures as an input, but that's not reality. If you scan something from a paper, or if you look at the depictions that humans are generating in papers, they are far from perfect. They are full of, forgive me, bullshit stuff that humans annotate to chemical structures. And and then came Otto Brinkhaus, who was on the honey cake horse picture, and he came up with the idea of RenDepict, which takes the chemical structures that we originally are generating and augments them with all the kinds of stuff that humans in publications do to their depictions. So it generates rotations, shearings, it adds more or less randomly arrows, which are often used to depict something. It adds atom numbers, which are often in chemical structures. It adds noise and all kinds of things. And of each structure that we are presenting for learning to the network, it generates 5 or 10 different depictions with different toolkits, different amount of noise, atom numbers, arrows, and so on and so forth. And it does this in a diversity selection-driven manner, so that also statistically we can assure that the system is seeing maximally diverse things. And that made the final breakthrough. DECIMER became so good at next slides that even it is able to do a reasonable job on hand-drawn chemical structures, although it has never seen any of those, which is, I think, quite a nice achievement. We've tested the system against a number of hand-created benchmark data sets. We have structures from the US Patent Office. The University of Birmingham created a number of benchmarks. The Japanese Patent Office has created a benchmark, and there are more, which can all be used to test the performance of the system. We tested the performance of DECIMER against all openly available, all open source OCSR tools on the market. I mentioned that these rule-based systems, which are based on vectorization, they are on the market for quite a while. And while we were working on DECIMER, there were also other groups working on deep learning-based systems, and those that published the data in an open source way were used in our evaluation. And you can see that based on clean data sets, we have them all reasonably close to each other. In particular, MolScribe and DECIMER are performing reasonably well. What is shown here in blue is the amount of identical predictions, so where the system got the answer completely right. And then in green, there is the average Tanimoto. And you can see that a Tanimoto of 0.9 is very close to 1, and the results are usually very good. But when you do something, these are our colleagues from Bayer in Berlin tested this, when you do very little change to what we call clean data, something like this here, and you augment the data, you shear it a little bit, you rotate it a little bit, then the performance of these tools typically breaks down. Yeah, in particular, the rule-based ones get a very low percentage of the of the identical predictions. And in particular, DECIMER is not breaking down much, if at all, because it has seen all these augmented data generated by RandyPict during the training. So it becomes very robust against these types of, it's called augmentations, but it's actually imperfections, right, that are added to the data set. Okay, so this is DECIMER running on a smartphone during a conference. Kohulan is taking a picture of a molecule on the screen. He's zooming in. He's pasting it into the DECIMER web app. DECIMER translates the system to the picture from the screen into a machine-readable structure. The result was, in this case, surprisingly 100% correct. And then you can use the web app, and this says search the detected structure on PubChem and look up the biggest database on the market to actually look the system up. So it's really how to say, a very usable system. We published this completely open source in a Dockerized way. It's very easy to run your own DECIMER server. If you want to do large-scale conversion of articles, of structures in articles to machine-readable format, you can do this using our Dockerized version and run it in your own system. A short diversion. It was very quickly noticed that this last version of DECIMER was actually able to even translate hand-drawn chemical structures, and that led my colleague Achim Zilesny at the Westfälische Hochschule to ask a number of his students if they would be willing to take a few hundred structures and redraw them on paper to generate a hand-drawn image data set. It was 24 of students who were actually willing to do this. And they became so excited that eventually they drew 6,000 structures, and that led to the creation of the DECIMER hand-drawn data set, where we have now hand-drawn images like this here, and the machine-readable structure, because they use this to draw the pictures. And that's a wonderful benchmark data set now to benchmark the hand-drawn performance of DECIMER. Probably in the interest of time, I'm going to jump over most of this here. A quick overview of the results. So we are using DECIMER segmentation, the DECIMER segmentation system to segment structures out of a PDF like this one from a natural product article that works very well. The images are then cleaned and transferred to DECIMER. That's all work also done by Otto Brinkhaus, who got his PhD and left the group already. Of course, sometimes you get things that look to the system like a chemical structure, something like this here, or even this can be mistaken with a chemical structure. Lines from diagrams can be mistaken with a chemical structure. So you also need something like a classifier to more closely inspect whether a segmented image is really a chemical structure or not. That's work by Isabel Agea, who came to us from Prague and did an internship. And she trained a very nice image classifier based on EfficientNet to be able to distinguish, I mean, this is easy, obviously, but to distinguish a chemical structure from a coffee cup and other non-chemical images. Okay, I think I'm jumping over this. A quick demo, if you want to test the system, go to decimer.ai, take a PDF of your favorite organic chemistry publication, upload it again, we use Journal of Natural Product. You see that there are lots of diagrams and some chemical structures. DECIMER segments out the images of the chemical structures on the fly and then presents a structure editor next to the image with its identified machine-readable structure. You can then look at it, modify it, and download the results. Yeah, so and again, if you're interested in this system, take the downloadable version. We are limiting this here to a handful of structures and 10 pages to not overload our server, but you can always run this system locally, and that gives a very nice result. So I think I'm coming to an end. I don't want to close without showing you a beautiful outcome of AI. This is an email from Kuhulan, who was testing DECIMER, was testing the Google AI Gemini. It's a large language model by Google. And he asked it, what do you know about DECIMER? And it generates these results. It knows everything about DECIMER, all the publications, what it does. That's very nice. He then said, okay, that's very nice, but can you also write me a song about the knowledge? And he took the lyrics and he gave it to Suno.ai, and Suno.ai created a song about our DECIMER system. I don't know if this is now going to work. If you can hear anything. Let me see. When you're looking for a molecule in a paper or a book, there's a way to save the trouble. Take a closer look. DECIMER's here to lend a hand, a marvel of our time. From image to a structure, it's simply so divine. DECIMER, oh DECIMER, you turn pixels into gold. In the world of chemistry, your story must be told. I spare you from the rest, but it's amazing. It's really amazing. The AI wrote the text, and I find the conversion into this pop song, which sounds so realistic, just absolutely amazing. So. Yes, it's actually it's on YouTube. If you want to hear it completely, it's really worth it. And yeah, this is my thanks. We are this is my wonderful group, and we are really very, very grateful to Google for making the compute time in the TPU Research Cloud available to us extremely generously. Without this, the whole study would not have been possible. And thank you very much for your kind attention.